analysis of a couple of questions we might have. And the first one is going to relate to binary trees, our favorite structures. Very simple, only have 2 children at most. And oftentimes when we have a binary tree and we have this invariant, the invariant looks like this: less than or equal and greater than. We call it, what kind of tree is that? Not a heap? Binary search tree. Less than or equal to, greater than. Okay. If we have a binary tree which is complete, and we have, let's say, something like this, then we'd say that's a what? That's a heap, right? Okay, so now, so that you could think of this as a less than, so maybe it's a min heap. If we have the other way around, it would be a max heap. Okay. All right, now, of course, the heap requires a shape too. Not just an invariant, but it requires a shape. The shape is complete. But let's talk about a tree. Let's say we have a binary search tree. So it's called BST, right? So let's say, what is the shape of a binary search tree? How many shapes are there in a binary search tree? I have to think about that one. So how many shapes? I don't know. Let's talk about, what do you expect the tree to look like? When I say what I expect the tree to look like, I mean, what does that mean? Why is it important what the tree looks like? What characteristics are important for binary search trees? Well, let's say they're not balanced. Let's say of a tree it's not balanced. And if you just think about it. If you take 1,000,000 random values and you insert them into a BST, is it going to be balanced?
It depends on value.
The answer is probably not. Probably not. If you have 1,023 elements to put into a tree, is it going to be balanced? The answer is probably not. Why not? Why am I saying probably not? Well, what would generate a tree? First of all, would you agree that if a tree of 1,024 elements was to be balanced? Did I say 1,023? I added 1. If this tree was going to be balanced, would you agree that the first 9 levels of the tree would be full? You would not agree? I would agree. If the tree is going to be balanced, then you better have every level full, and then this one may have some missing stuff, and only at the bottom level. Does that make sense? Are you with me so far? So, 1,023 nodes means that 512 of them are in the top. Remember, log of 1023 plus 1 is 10. So there's 10 levels of this tree, right? 9 of them are full. And the last one is missing nodes, making the tree balanced. Well, 1023 would be full anyway, right? Because if it would, 1023 could be full. We're saying that, what's the probability that a tree of 1023 is balanced? Well, the probability is that 512 must be full, and then this level, so 1023, 1022, anything over what?
5.
Anything, so that means the first 512 have to make a full, right? And then we have to have values such that the last 511 are only going to go here and here. What do you think is the likelihood of that happening? Do you think it's very likely that they're just going to happen to go right here? You're going to happen to have one that's the smallest in the whole tree. You're going to have one that's largest in the whole tree. You're going to have one that's larger, smaller, smaller, larger, smaller, larger, smaller, larger, smaller. They have to be just right. Okay, you don't want to answer my question. That's all right. That's not a very good question anyway. Let me ask you this. Suppose I am inserting 512 nodes in a tree, so n is greater than 512, but n is less than 1023. Are you with me on this one? And now, so therefore the number of nodes in this tree is n. And I'm asking you, what's the likelihood that this tree is balanced? And your answer is, not very likely. You know why you're saying that? Because it's probably true, and it's not like I can say wrong, because you're not giving me a number. So it's a safe answer, and it's probably right. But now I want to think about why that may be probably not true. You guys know how nodes are added into the binary tree? Some of you are weak on data structures. Who knows how to add a node into a binary tree? Okay, can you explain to all of us? How do you add a node in a binary tree? You can sit down, you can just talk. You can stand up and talk.
I can do something.
No, I want you to use language. Okay. So we start at the
root node.
And then we say,
if you got any new node, just compare with this root node. If it is less than, come left side. If it is greater than, go right side.
Okay, and then I go over here. I go, it's less than. So now I say what? Are you less than or equal to? Less than or equal to, or greater than? If it's greater than, you go here. If it's less than, you go here. But there's nothing here. Oh, then you add it here. So every new node in a binary search tree is added where? Every new node that's added in a tree becomes a what? It becomes a leaf. It becomes a leaf. Which means what? No children. That's what it means to leaf. No children. So if n if n is a value greater than 512 and less than 1023, then this tree cannot be full, correct? Because full trees can only be 511, 1023. And this is less than 1023 and more than 511. And there's no, so it cannot be full. That's not a bad thing, it just can't be full. But can it be balanced? Of course it can be balanced. What's the likelihood of that tree being balanced? Well, trees, the nodes are always added at the bottom. So there are many ways to produce a balanced tree of n nodes with this range, many ways. But one way we could do it is if we happen to generate a full tree of 512, right? Correct? And then we happen to be lucky that we don't, for example, what's the minimum value of the tree? It's right here. That value is 23. So that means we have to have only one value that's less than the minimum, and one value that's more than the maximum, and one value that's more than the old maximum, but less than the new maximum. You feel what I'm saying? So that could happen. So in order for that to happen, then the tree has to be generated as full. The 512 has to be generated as full. What's the probability of a tree of 512 to be generated full? What's the likelihood of that? Well, funny you should ask. So we have not 512. We really should call this 511, right? This should be 511. Okay? And then we have 512 here, making it 1023. Stand corrected. Okay, so let's see what that would take. Well, first of all, so I have so let's say I have 511 values. So let's say k is equal to 511, and that's what I'm going to do. I'm going to add 511 values. What's the probability that that's going to be a full tree? Well, the first thing that has to happen is the root must be inserted when? First, second, third, fourth, fifth? Last? First. If you insert the root always is inserted first because it's an empty tree. So you add a node, it's going to be the root. It'll never not be the root. It'll always be the root. we're not deleting, so it will always be the root. So therefore, we must have a root selected such that everything on the left and everything on the right has the same number of nodes. So if that one node is here, we have 510 nodes left. That's 255 nodes, and they have to be, half of them have to be less than this, and half of them have to be greater than that. Which means that the root has to be the element in the middle. So if we consider an array that has 511 values, okay, and we take the middle element out, and that happens to be the root element, then that element would be really good, because then all the values to the left might go to the left subtree. This could be, and that's the only way it's going to work, because of this invariant. Less than or equal has to be here, so therefore let's put all those guys into this subtree, and all those guys into this subtree, and then we have a balanced tree, or a full tree in this case, right? All right, so now what, if you're doing this at random, what's the probability that that happens? In this particular case? 1 out of 511, that's a difficult number. 1 out of 100 is 1%. 1 out of 500 is 1/5 of 1%. 1/5, what's 1/5? 0.2, right? So it's going to be 0.002, right? What's that probability about? That's the probability that at random you will select 1 out of 511 nodes, which will be the middle node. Is that high probability or low probability?
Low probability.
Okay, that is 2 out of 1,000. But then, not only that has to happen, but then I have to select the left child and the right child. The left child and the right child. And the subtree of the left child and the subtree of the right child also have to be the same. Which means that after you select this one and you have this remaining for the left subtree, you better pick exactly the middle one here. What's the probability that we pick this element as the left child out of all those remaining values?
1 out of 255. 1 out of
Well,
100.
hold on a second. Hold on a second. So the probability, first of all, the reason we got this one here, we didn't exactly partition around it. I'm just cheating. I'm putting the array in order. It's really not in order. I hate to tell you that. So basically, we have this, the probability of this is really, so we want to add this, so this element has to be added number 1. But this element has to be added what? Now what about this one? So actually these two are both number 2. Because we can add this one as the right child first, or this one as the left child first, it doesn't matter. But we cannot add any other values first. Meaning that before we add a 4th value into the tree, these values have to be added. This has to be the first. This is 2 or 3, or 3 or 2. Or 2 or 3, or 2 or 3. This one. So what's the probability that we select one of these 2 elements as the second element to be inserted into the tree?
2 or 5.
So 1 out of 511 was for the root. And then this one right now is what? 2 out of?
510.
2 out of 510. Because we can select this one or this one. What's the probability that we select the other element next?
4 into 5.
Suppose I selected this one first. And I selected this one second. The probability of this one was 1 over 511. The probability of selecting this one or this one was 2 out of 510. But now I've selected it. Now what's the probability I'm going to select the third one as given?
1 over 5.
1 over 509. What's 1 times 2 times 1? 2. What's 511 times 510 times 509? Really big number. What's going to happen with these numbers? Really, really small. What's going to happen with these numbers? Really, really big. Okay, so I don't know how much is 511 times 510, but I do know that this is half a k, which is, so we're going to call it 2 to the 9th, which is 512, right? This is about 2 to the 9th 2. This is about 2 to the 9th 2. You know, plus or minus a couple points between friends, not a big deal, right? So what's 2 to the 9th times 2 to the 9th times 2 to the 9th? 2 to the 27th. So what's 2 over 2 to the 27th? I don't know that, but I do know 2 to the 27th is 128 billion. So this is 1 out of 64 billion chance that that's even going to happen. So what I'm trying to tell you is it's pretty unlikely. It's pretty unlikely to get a full tree. And you kind of have to have a full tree in order to get a balanced tree. There's a relationship between them. If your tree starts going crazy like this, if 11 nodes deep, it's over. Because here, you can only have 10. If you just have 11 in one place, it's over. Anywhere, 11. Anywhere. How would you create an algorithm to create a full tree given the number of nodes n equal to 2 to the k minus 1? So that's 511, for example. What would the algorithm look like? Well, the algorithm would have to kind of do this. Let's write this algorithm. Okay? So let's write this algorithm. So we're going to create an algorithm to create a full tree out of 2 to the k minus 1 equal to n nodes. Okay? Everybody understand what we're doing? How about you guys in the cheap seats over there? Good? These are the best seats right here, most expensive. She's got a season ticket. That's a good one, right?
Professor,
All right. Yes?
if there's a simple question like if there's 512 or 1024 nodes, can we create a balanced tree? The answer is simply no.
No.
Because
The answer is simply yes. I'm not talking about whether we can do it or not. We can. Every tree can be balanced.
okay, even if it is ordered.
If you look at the elements of every tree, that tree can be balanced. The question is it going to be balanced? A different story. So now we're going to create just create a full tree with 2 to the k minus 1 nodes. Okay, so coming into this tree, what we're going to have is we're going to assume that we have a BST, and this BST is empty initially. Okay? So what I'm going to do is I'm going to have a function, I'm going to call it BAL for balanced. Or maybe I'll just call it full. Let's do full. So I'm going to send into this function an array, and the array I'm going to assume that the elements that I'm going to insert in the tree are sorted. Heap sort. Merge sort. You talk radix sort this semester? Radix? Talk about radix. Bits. Okay. So we're going to just not worry about it too much. So full, and then we're going to have array A. We're going to call it A. And then we're going to assume that it is 2 to the k minus 1. Size, that's going to be n, but we're going to have, let's use this, let's call the array X, because I want to use A. So then I'm going to have, so array will be X, and then I'll have A and B. What will A and B be? Those will be starting, we used those before, right? And then, and then we can assume, for example, we're going to have our tree is going to be T. And initially it's going to be empty. But it's going to have its own methods, like insert. So when I insert, it's going to insert it correctly. Okay, so what kind of, is this going to be an iterative algorithm or a recursive algorithm? Why? Because I don't know how many times I'm going to be iterating, right? And a binary search tree is a recursive structure. You have a root with a left subtree and a right subtree. Well, every node is a root of its own subtrees with the same invariant. Okay, so the first thing we're going to do is, so let's think about a very simple example. A very simple example would look like this. So let's say I have 1, 3, and 8. So this is the array X. This is the array X. This is A. This is B. What do we want to do? So again, and we can index this 0, 1, 2, 1, 2, 3. It really doesn't matter. Okay. So what is the middle going to be?
B by B.
A plus B over 2. So if this is 1, 2, 3, that's going to be 6 divided by 2. We get 3. 3, 4, 5. Oh.
4 by 2.
Wow. He gets extra points today. 3 plus 1 divided by 2 is going to be 2. That's the middle. Let's see if that's going to work generally for these arrays. So let's say I have 1, 2, 3, and then I have element 4, and then I have 5, 6, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, correct. So if I have 5, 6, 7, what's 5 plus 7? Divided by 2?
6.
So that works. Notice that this is an array of 7 elements, where 7 is 2 to the third minus 1. Okay, so just want to make sure if we're going to use this assumption, we can take care of this. Okay, so basically what's going to happen with 7 elements, I am going to insert this element first. Okay, so what's the first thing I need? So it's going to be insert this first. So what's my base case?
A should not be greater than. The array should not be empty.
And, correct, and we're going to judge it by?
A should not be.
What's the condition of not being empty based upon A and B?
A greater than B.
A
Greater than B.
should be what?
Less than.
B should not be greater than.
If A
A
greater
should
than
be-
B, less than false.
What's the smallest size of array that we're going to accept for doing something?
Single
1. So what's the condition of A and B in that case? Equal. So what's the condition of the array being empty?
less than equals. Less than 1.
So condition is going to be if A is less than or equal to B, then there's something to do. Else what? Else A is greater than B, there's nothing to do, the array is empty. Right? So if A is greater than B, what do we want to do? We have to calculate the middle index. So we're going to say M is going to equal to A plus B, and I'm going to say div 2, although div just means division, integer division. So that's going to give me an index. Now what do I want to do?
Match to the left side and
We'll put M into
then match to the root. Middle element should be matched with the X.
I'm not matching.
Make M as a.
I'm just inserting in the right order.
We will M as a.
Because, for example, if you look at the elements, for example, well, I'm going to, let's say 5, 1, 7. If you insert those into a tree, you're going to get 5, you're going to get 1, you're going to get 7. If you have 1, 5, 7, you're going to get 1, 5, 7. If you're going to get 7, 5, 1, you're going to get 7, 5, 1. So the way the tree is balanced or not depends upon not the numbers themselves, but the sequence or the chronological order of the insertions. So all I have to do is I have to just pick the right insertions at the right time. If I pick the middle element right at the beginning, it's going to become the root when I insert it. So since I've picked the element which exists, then all I need to do is I need to go to the tree,
Make it as a.
and I'm going to say tree, insert, right? insert, and all I'm going to do is I'm going to insert, what am I going to insert? I'm going to insert array element x sub
M.
x sub m, right? So insert element x sub m. You can use brackets if you like. It would be more like a computer programmer. Okay, so insert x sub m. So now what do we want to do? We're recursive, so go ahead, a little bit louder.
Go to the left and go to the right. So
Okay, so since so we know the array. So what I've done recursively speaking, I basically selected this element. So what I want to do is I now want to recurse full with the left side, and that's going to insert the middle of the left. I mean, if I gave you the whole array and inserted the middle of the whole, then if I go full, what? So what is the left side of the array? It's going to be x, a, m minus 1, and still the same tree. So let's see what's going to happen here. So what's going to happen here, so let's say we have 7 elements here. 1, 3, 8, 11, 12, 15, 22. Let's see what this tree, how this tree is going to get built. So it's going to get built right away. This one is going to insert what? 11 is going to get inserted, and now we are recursing. We're recursing with from 1 to 3. Because m was 4, so it's 1 to 3. So that's, now we're calling recursive level 1 to 3. The condition is true. 1 plus 3 is 4, div 2 is 2, m is 2, insert x sub 2, x sub 2 is 3. We insert 3, 3 is less than, that's the invariant, right? So we don't worry about that, the tree does that. We just call the right sequence. Okay, and then what we're going to do is do what? Then what we're going to do is we're going to insert, and then we have to follow this recursion. X, A, and now m was 2, so it's going to be from 1 to 1. So now we're going to go recursive level 2, 1. So this originally was 1 to 7, now it's going to be 1 to 1, right? 1 to 1. Condition is?
True.
True. 1. Insert x sub 1. That's going to be a value of 1. That's going to come out here, correct?
Correct.
Okay, but now we're done. We are at recursive level 0, recursive level 1, recursive level 2. When we finish recursive level 2, we have to go back to recursive level 1. Last time we were recursive level 1, we inserted the 1. So now I think we have to insert element 3. How do we do that recursively?
X plus 1, comma b, comma d.
So it's going to be a recursive call to full array x.
M plus
And now instead of going left of the m element, we're going to go right. So we're going to go m plus 1
b.
to b of t. So let's now go back to recursive level 1. Recursive level 1, which had a value of 2, sent 1. Now it's going to send 1 plus 1 is going to be 3 to 3. That's a single element. It's going to insert the third element, which is 8, which is going to go here and here. After we finish, that's recursive level 2, we go back to level 1. After we did level 1, we inserted everything we had to insert, so we're going to go back here. Now we're at recursive level 0. At recursive level 0, m was equal to? 4. So therefore, after the insertion, we've already went to the left, so now we're going to go to the
Right.
Remember, the way we got from level 0 to level 1 was from here, so when we come back to level 0, we're now going to continue with the next instruction in sequence, which is going to be the next second recursive call. M here was 4, so this is going to be 5, 2, 7. 5, 6, 7. So we call 5, 6, 7. This is going to be 5, 6, 7. condition is true, m is equal to 6, we insert 6th element, which is 15. And then we go from here, from 6, we're going to send in 5 recursively. By the way, after we send in 5 recursively, we're going to insert 5, and then we're going to send 5 and 4 for A and B, which will generate recursive level 3, which will be a base case. Nothing to do. Every time we insert with a 1, it then calls 2 recursive cases, where basically each of them is going to be 0 elements. You follow what I'm saying? Or no? If you don't, I'll show you that in a second. Okay. So what's going to happen here, once I do that, then I'm going to recursively, so it's 5, 6, 7, put 6 in, and then I basically, since 6 is m, this is going to be a to m minus 1, this is going to be m minus 1 to b. So it's going to insert 5 next, 5, element 5, which is 12, which is bigger, smaller, 12, and finally it's going to insert element 7, which is bigger and bigger, and our tree is full. And we feel happy. We did something good. Okay. What's the complexity of that anyway? What's the complexity of the algorithm? What is the characteristic operation? Okay, isn't really the insert the characteristic operation? But, here's the tricky thing. So we can think of the characteristic operation as one operation, but in reality it's really not one operation. And the reason for that is because it's one operation for us, but it's a different level of complexity for the binary search tree, because as the tree gets bigger, an insert has to go down lower. But we can consider it as one right now. So therefore, if we do this now, so basically t of 0 is equal to what in this case? How many inserts on an empty tree? 0. Empty tree, 0 inserts. We won't insert anything. It'll just be empty. Okay. So now we have t, and we are using t of n, but I'm going to write it as 2 to the k minus 1, right? Because, okay, so we're going to have one insert, so it's going to equal to one insert plus, these are the same. So this is 1 in, what the heck is this? Plus? Okay, so it equals to 1 plus. These are the, how come these are the same? Because I made it so that they're always the same. Left and right, they're always the same. So it's going to be 2 times t of what? 2 to the k minus 1 minus 1. That's the recurrence. Yes?
Is insert actually like log n complexity?
Well, that's a good question. How can we find out?
Because you swap down.
How can we find out? We can find out if insert is an average of log n by counting the average depth of these nodes. Because the depth of the nodes is the number of comparisons you make on insertion. The root had 0 comparisons at level 0. These guys had 1 comparison with the root only. These guys needed 2. 1, 2 ended up here, 1, 2 ended up here, right? So if you count the number, so what we want to do is we would like to generally find out what is the average depth of a node, and we've done that. Half the nodes have a depth of log 2n. A quarter of the nodes have a depth of log 2n minus 1. An eighth, right, a quarter of the nodes, log 2n minus 2, etc., etc., etc. So we have that. Go back in the notes, and you'll see what that operation is. The average depth of a node is, and that applies for a full tree. For full tree. Nobody remembers? Nobody remembers? What kind of students are you? Just kidding. Don't take it personally. Just making a joke. Okay, so nobody recalls exactly what it is? Okay, don't worry about it, but look it up. Look it up, because you need to know this. We did an average depth of a node in a full tree, which was a nice analysis. Now, so what is the complexity of this one? Would you agree that this complexity is, roughly speaking, T of n is equal to 1 plus 2 times T of n over 2? Would you agree that that's a good approximation? You're looking at him like so. He trusts you. You can tell him anything, he'll believe it. Okay. Would you agree that this is a good approximation for that? Because 2 to the k minus 1 is basically the best half we can get after you take one element out. So it's a good approximation. What can we do to solve this one? Master algorithm, okay? So that's going to be n to the log base 2 of 2. That's equal to n. So what's the complexity of this algorithm? It's n. It's n. Because what's f of n? What's the actual work at level 0? 1. So this is going to be, so it's rising exponentially up to n. So therefore, the leaf level captures everything proportionally. So so this is a very efficient algorithm, but this algorithm is going to be basically hitting that tree. So that's a whole other thing we have to see. Okay? Yeah.
Back to the previous, like you say, the insert was based on the average depth. And
Yes.
The average depth is a constant, so the insert.
How's it constant? No, not a constant. For example, if you have a tree, if you have, for example, 511 nodes, the average depth, these guys are at depth 9, but this is depth 0, so there's going to be 256 times 9, 128 times 8, right? All the way down to 1 times 0.
Yeah, so it's not a constant. So but still, its insert still count as 1 as data.
No. I'm just saying from the standpoint of this algorithm only. If we just count this as 1. If we count it as 1. Now, in reality, so we solved this recurrence as this was 1. That's it. But in reality, it's not going to be 1 because we have to do the insertion.
If that's not 1, then the complexity will change.
Correct. By the way, I could make the complexity 1. How could I make the complexity 1? How could I be that powerful? And so can you. How can I make the complexity 1 for the actual insert? What a great question. Could it be 1?
Geometry is empty, we are inserting complexity.
Do we know when we're adding so for example, which is the sequence of nodes? This is the first node to be added, correct? This is what node to be added? Second. This is the third. This is the fourth. Okay? How can we figure out where they're going to go in the tree? And the only way we could do it is if we're using an array as our tree. Because it's full, we can use an array, just like complete can use an array, but full is complete. Because it's fully complete. Nothing missing. So if you know, for example, that the number of nodes you have in the array is 7, you can figure out the sequence of additions. And if you can and you know which way they're going to go. So whenever you do this, you're always going to go 1, 2, 3, 4, 5, 6, 7. You're always going to go that way. And if you can do it for 7, you can do it for 1023. Just put them in the right array spot. So you need to keep track of the sequence you're adding and compute where that's going to go. We can make it theta 1. Now, of course, so we can make it theta 1 here. However, I don't think it's a great idea all the time, because then we can't really mess around with this tree very well unless we keep it complete. Because once it's full, it's good. If it's complete, it's good. But once we start having stuff over here, then we have a problem. Okay? All right. So let's leave this at this point. Now, the second question I wanted to ask, I have another thing, a couple things I want to talk about related to BSTs. Let's see what we have time-wise. Okay. I have some notes on the overhead, but I think we'll just kind of go to, we'll just kind of see if we can go to something else on the board, because the board is so much fun. Plus it's illuminated. Maybe I can turn this off. Now we have a more dynamic board. Well, the other thing I was talking about really is, so we understand so whether or not a tree is balanced is not a function of the values in the tree. It's a function of what? Of the sequence of insertions. Could you prove that? Could you prove that any sequence of numbers could be made into, let's say, any sequence of unique numbers? Make it easier so there's no duplicates to worry about. Any sequence of unique positive integers could be made into a balanced tree. Could we prove that? Well, suppose you have n elements, n element array. You can always sort it, correct?
Yeah.
Okay. If it has an odd number, then picking the middle element will always be the correct one, because then we'll have an even amount of values that can go into the left and right subtree recursively. If it has an even number, then we can basically pick one element or the other element, the maximum of the left half or the minimum of the right half, and that's going to be fine, because then the tree will only be off by 1 on the left side and the right side, and we're allowed to be off by 1. Okay, so if we just keep it to always being odd, then we can use the argument of 2 to the k minus 1, because that's the only way we're going to always be odd. When we take 1 out and the other 2 halves are going to be odd. It's the only way we're going to have it. So, so in this case, if we pick the middle element, we'll always have it in half. So then recursively, we'll always pick the middle of the left and right, which are also odd, and then they will have left and right even, and recursively so, until the division of the odd goes down to left and right being 1, and then you put them on the left and right side. So we can always create it, so it's a sequence, right?
Yeah.
But you have to have the order first, and then you pick correctly. You pick correctly. But what do we expect this tree to actually look like on average? Because that's sort of, again, we saw the algorithm, but we also saw that randomly, this is extremely unlikely. The probability of that actually happening, what we just did here, is extremely unlikely. Right? By the way, did anybody figure out what is the average depth of a node in a binary search tree which is full? N log n. N log n. And what was the complexity of this algorithm?
N.
And the summation of all this work is n. And the summation of all the insertion work is n log n. So what's the theta complexity of this? N log n. Because you take the maximum. Because it's plus, not times. Not a loop, right? You do this and then you do this. So you're doing this and you're doing this. So the cost of building this balanced tree, or this full tree in this case, is n log n. Which is pretty good. N log n is the, hold on, n log n is a summation of the nodes, right?
Yeah.
That's a summation of the work. So that's why this is an n log n. So what's the average depth of a node? Log n. Because there are n nodes divided by n log n divided by n, log n. That makes sense. 50%, it's 0.5 log n. Plus 0.25 log n minus 1. Plus 125 log n minus 2. That will be proportional to log n. Okay, anyway. Now, suppose the data is coming in randomly. So we have random data. We take an array of 1,023 elements or whatever, and we randomly pick one. We randomly pick, we mark it as picked so we don't pick it again, and we insert it. And we randomly pick again, and we insert that. Is that tree going to be full? You realize the probability of that is almost, is practically not going to happen. It's not likely to happen. It's not going to happen. Don't bet your money on it. It's not going to happen. So the question is, what can we expect? I mean, it could be horrible. If the data is already coming in sorted order, for example, then you're going to get a skew tree, and 1,023 is going to become a list of 1,023. It's coming in descending order. It's going to be this way. But there's a lot of other skew trees. Like, for example, you start here, and then you have, this one is bigger, this one is bigger but smaller, this one is bigger but smaller but smaller, bigger but smaller but smaller but smaller. So you could have a lot of skew trees. I mean, completely skew trees. Skew trees are trees where the height of the tree is essentially equal to the number of nodes. That's a skew tree. We can count the number of skew trees if you want to. That's a fun exercise. But I'm more interested in another kind of counting. I'm more interested in counting, for example, the number of shapes that binary trees can be in. So we can do that little exercise. And then another time we can figure out what do we expect as the expected height of a tree. And what is the expected depth of a node with random data coming in. That's more useful. But we have to have a baseline to start with, and that's our baseline is what we did here. So let's talk about shapes of binary trees. So now we're going to forget about the values completely. We're just going to look at the shapes. And we already know that the shape is determined by what again? By the sequence of insertions. That's it. Okay, so if we have a tree which is empty, and I'm gonna draw it like this. So basically, it's a root pointer, which is null. There's only one shape for that tree, and that is an empty. There's no nodes, right? Okay, that's kind of boring. If I have one node in a tree, how many shapes does that give me? It's only one, because it can only be a root pointer to a single node. That's it. There's no other nodes. If I have two, however, then I have a root, but I can have a left child, or I can have a root, and I can have a right child. So we go from 1, 1 again, and this one has 2. So where the number of nodes in the tree is 0, 1, and 2. Now this looks like an easy exercise, but it gets very hard extremely quickly. If the number of nodes is 3, then basically what it means, you can start with this one, which is only this one, and you can continue in this direction. And you can start with this one, and continue in this direction, because that's a null pointer, that's a null pointer, but that's also a null pointer. So that means you can start with this, and then add to this null pointer, and that's the third shape. But you can also then have this, which is 0 here, like here, and then you can have one that's going to the right, or you can have one going to the left, or you can go this way, and then add to this null pointer, but you can see that this one is a repeat. So we're not going to count it, because we're not counting. Now you understand that these are different trees, but they're the same shape. And shapes are important because shapes give us an accounting of what can happen. What are the possible shapes that can give us? So here, the number of nodes we have is actually 3, and the number of shapes we have is 5. Now, it's actually kind of hard to even answer the next question, and that is how many trees do you get if you have 4 nodes? How many different shapes can we have? Because now we have to take all of the possible 5 3s, okay? We want to add them. So we take this one, and you look at all the possible ways you can add a fourth node. 1, 2, 3, 4. 4, 4, 4, 4. There's 20 different ways I can add a node, but some of them are going to be the same, so I have to look at them all, and I have to cancel the ones that are duplicates, because I'm counting shapes. So I know it's going to be less than 20, assuming that there's a duplicate, and I can probably generate a duplicate pretty easily. Right? What is the formula for number of shapes for 4, 5, how about 10? It gets crazy, right? So, but how would we do it? So let's think about how would we do it? It's not obvious. Would you agree with that? It's not obvious, right? It's not obvious. So most people would do it this way. They would say, how do I do it without having to cross out the same ones that happened before? How do I utilize what's already been done before? The way to do that is basically you add, but then you utilize it with a previous known result. So for example, let's consider a tree that has height 4. If a tree has a height of 4, it means it consists of a root at least, right? But then it has to have a left subtree and it has to have a right subtree. Would you agree with that? And because of the recursive structure of the right subtree and the left subtree, because they're also trees, their total number of nodes has to equal 3. Which means that you might have 0 nodes here, but if you have 0 nodes here, you must have 3 nodes here. Does that make sense? Or you may have 1 node on this side, which makes 1, this is 2, so then you would have 2. Or you might have 2 here, which makes a total of 3, then you must have 1. Notice what's going on here. Or could you have 3? 3. So 1 plus 3 is 4, then you must have? Could you have 4? No, because then the tree would have 5, I already have a root. So these are subtrees. So I create this kind of relationship. Now, what the heck is that telling me? Well, I know about the different shapes with 0 and 1 and 2 and 3 and 3 and 2 and 1 and 0. So would you agree that we have described here all the possible ways, not shapes, but ways that we can have subtrees of a tree of size 4? Okay. So now, let me ask you a question. How many shapes could the left subtree be in when the left subtree is 0?
1.
So we can say, in a sense here, is that S of 0 is equal to 1. The number of shapes with 0 nodes is equal to 1. The number of shapes with 1 node is equal to 1. The number of shapes with 2 nodes is equal to 3. And the number of shapes with 3 nodes is equal to 5. So therefore, if we take this into consideration, we would have S0 on the left subtree and S3 on the right subtree. Would you agree with that? Yeah? What is S0?
1.
So that means that the left subtree would have exactly 1 shape. But the right subtree would have exactly 5 shapes. So 1, 2, 3, 4, 5. But this one is always... So those 5 shapes always matching with this 1 shape. So it seems to me that 5 is the total number of shapes we could have in the left subtrees and the right subtrees together. Based on the second pair, I would have S1 and S2. S1 is equal to 1, and S2 is equal to 2. So this is always the same shape. Always the same shape. It's 1 node. But this is two different shapes. So these two different shapes are being matched with one shape. So therefore, this is going to be equal to 2. Because this is always the same, but this is once, twice. So this is staying the same. One shape, two shapes. Next one is S2 and S1. We already solved that problem. That's a 1, that's a 2, that's going to be a 2. And the last one is S3 and S0. We already solved that problem, and that's going to be equal to 5. When you add these things together, you get 14, which is the correct answer. So S of 4 is equal to 14. And now we're going to calculate S of 5, which is going to be the most interesting one so far. So S of 5. Well, again, we'll do the same kind of analysis. So we know what the values here are. S of 5 is going to have basically a tree that has 5 nodes, has to have a root. And then it has to have 2 subtrees, 1, 2. So therefore, we must have 4 nodes in between the 2 subtrees that could be 0, 1, 2, 3, or 4. But if this is 0, this is necessarily 4, and 3, and 2, and 1, and 0. So what we're going to have is S5 is going to equal to, now notice what we're going to do here. So 0 and 4, this is going to be 0,
14.
and this is going to be 14. So what's that together?
14.
14, because S of 0 is 1. So it's going to be 14 plus. Now we're going to have 1 and 3. 3 is what?
5.
So what's that going to be? 5. Now watch this one. This is where it gets fun. So 2 means that the left subtree has 2 nodes, and 2 nodes can be in 2 different shapes. That means for one of those shapes, this can be 1, 2. And for another shape here, this can be 1, 2. So the total number of shapes is going to be what?
4.
So we're going to have 4. And then we're going to go 3 and 1, and that's just going to be 5. And then 4 and 0, that's going to be 14. You can sort of see it. Okay, so we've got 28, 38, 39, 40, 42, which is correct. 42. So S of 5 is 42. So now that we understand sort of the process, you can probably figure out S of 6 without too much difficulty. Get the idea? 5, 2, 2, 5, 14. So what we have here, so S of 6, let's see if we can write this down. S of 6. So 6 is going to require 0, 5. So that's going to be what? 42. But it's really going to be 0, 5. So this is going to be 0, 5, and also 5, 0. So it's, let's say 2 times 42. 1, 1, 4. 1 is 1. 4 is 14. So that's going to be 2 times 14. So this is going to be 0, 5, 1, 4. This is going to be 2, 3. Is there a 3, 2?
2 times.
So it's going to be 2 times and 3, 2. So 3 is 5, and 2 is 2. 10. So 2 times 10. So we have 0, 1, 2, and 3. Do we have 3 and 2? It's already done, right? So we have 84 plus 28 plus 20. So we have 104.
135.
Is that 132?
2 times 5.
3 and 3, 1 plus 1.
Plus what?
3, 3.
2 times 10 or 2 times 5.
We cannot have 3, 3.
6. Yeah.
0, 1, 2, 2 and 3. We don't have 3 and 2. We don't have 4 and 1.
3 and 2.
We don't have
5. Yeah.
5 and 0. So is that the right number? 84, 28, and 20, so that's going to be 104.
130.
It might be right, I think it's better.
Yeah, that's better.
Okay. So now, what is the notation for this? So we want S of n. And so S of n is going to be equal to the summation as I goes from 0 to
N minus 1.
n minus 1 of S sub I
into P of
times S of n minus 1 minus I. And so this has a name. And this type of a number, this is called a Catalan number. And it grows very, very, very quickly. Okay? It goes very, very quickly. And so the number of shapes is extraordinarily large. I could ask you for a homework assignment that, for example, to count the number of shapes only of the skew trees. And a skew tree is a tree whose height is equal to the number of nodes. You can have, remember, you can have this, you can have this, you can have anything that goes down by one level each time. Whatever. So you have to count them. It's a great homework assignment, right? Okay, and so the probability of a skew tree is equal to the number of skew trees divided by the number of total shapes. That would be probably a skew tree. Don't worry about it so much. But that's just an idea. So these are called Catalan numbers. It's a very, very interesting problem, but you can see that we solved a pretty hard problem by looking, rather than trying to grow the tree downwards, we basically used the tree that we solved as the solution on the bottom. So we didn't change anything on the bottom, we only added one on top. And then we looked at the possibilities on the bottom, which were already known values. And so we're lucky we didn't have to do the crossing out. Because could you imagine, if you got 132 of them, if you got 132, imagine you have to cross out 57 of them. I mean, we can't do it. Okay, goodbye.